improves the precision, improves the accuracy, improves the detection limits, and so gives you much better measurements than the silicon.
Hi, Bom. Thank you for joining us today. As the Chief Scientist of AMPTEK, you have been involved in the development of SRF systems detector all the time. Today, we wanted to talk about FAST SDD detectors. Why they are becoming increasingly important in precision metal analysis. Over many years, detector technologies in SRF has evolved significantly from proportional counter to sapien to detector, now to SDD and the FAST SDD. Can you briefly describe this evolution and what motivated those technological transitions?
So what's happened is there's been, over about the last 35 years, been a process of applications driving the need for better detectors, and then the better detectors enable more applications, which continue to drive better detectors. So about 35 years ago, most XRF systems were only in the lab. They were very simple proportional counter systems that had limited usage, mostly in the mining industry. Then about 35 years ago, the need arose for portable instruments, particularly to measure lead in paint. And the lead in paint needed a better detector, so AMPTEK introduced the thermoelectrically cooled silicon pin for lead in paint. Once those detectors were used for that, though, our customers found other applications, alloy analysis, things like that, but to do that well required better detectors. So that drove us to a next generation of silicon pins. Those instruments then found new applications, which required better capabilities, which led us to the SDD, and then again, new applications were driving new detector needs, which led us to the FAST SDD and where we are today. So the evolution of applications has driven detector needs, which has enabled new applications, further driving better detectors. And it's worth noting, my focus today is the detectors, but along with the detectors, improvements in X-ray sources and signal processing electronics, analysis software, have all gone hand in glove to bring us to where we are today in XRF.
Okay. Now, many people are hearing about the FAST SDD detector. From a scientific perspective, what are the most important differences between FAST SDD detectors and the traditional sapien detector? And why are those differences important in practical measurements?
So there are two real differences between the FAST SDD and the silicon pin. The FAST SDD detector, they're both silicon photodiodes, but the FAST SDD has a more complicated electrode structure, and technically what that does is leads to a lower capacitance. That's important because the capacitance is really what determines high-frequency noise, so lower capacitance allows lower noise, which gives better resolution and much better count rates. In addition, the FAST SDD has a different kind of input transistor. Instead of a traditional JFET, a custom CMOS ASIC, and again, this reduces the noise at high frequencies, which allows better resolution and higher count rates. So that's the technical difference, but the implication of that is that the FAST SDD can operate at much higher count rates, and that improves the measurement quality, improves the precision, improves the accuracy, improves the detection limits, and so gives you much better measurements than the silicon pin.
Okay, thanks. Precious metal alloys are usually tested by SRF instruments. However, those materials can be very complex, often contain like gold, copper, and silver, and palladium and palladium. What is detector performance important when analyzing these materials?
So when you have a complicated spectrum like that, the challenge is some of these elements have multiple emission lines, and the lines are closely spaced and they overlap. And that overlap degrades the accuracy and the precision and the detection limit, particularly detecting minor amounts of materials. In an application, you may have a small amount of platinum. Much of the value may be in the small amount of platinum. And so measuring that well, you want to separate these overlaps, and that requires both the high energy resolution, the better energy resolution, and also high counts. The more X-rays one counts, the better the precision. So it's the FAST SDD's ability to have both better resolution and operate at high count rates and memorize spectral distortions that allows one to separate these really complicated spectra with overlapping elements, and particularly to do an accurate measurement of the minor elements, which are so important in precious metals.
Okay, thanks a lot. Energy resolution is often mentioned when discussing the detector's performance. For non-experts, can you simply explain how better resolution helps analyze precious metal alloys?
Sure. So energy resolution is the fancy technical term that basically means the width of a line. So you have characteristic X-ray emission lines, and they can be closely spaced. And if your energy resolution is poor, those lines are not resolved. There's just one big blob, and it's difficult to accurately quantify the amount of those elements. So a better resolution turns one big blob into separate peaks, reduced overlap, and that allows a much more accurate quantification of the material that's present. So energy resolution leads to separating overlapping peaks, which leads to improved detection.
Okay, thanks for your answer. I want to ask the next question. Precious metal usually produces strong fluorescent singles. When these singles are very intense, and the detector must process many events quickly, how does FAST SDD maintain accuracies at high count rate?
So it's a good question, and it really gets back to that slightly technical answer about capacitance and noise. In a silicon pin detector, because there's so much noise at high frequencies, if you run at a high count rate, the resolution gets poor and artifacts are introduced. The FAST SDD has much lower high frequency noise, and that enables it to maintain the energy resolution at high count rates, minimize the artifacts, so you can operate at much higher count rates. That's what the name FAST SDD comes from. It's fast because it enables fast measurements and high count rates. And it really all derives from that high frequency noise, which is from the structure of the detector and the input transistor we utilize.
Okay, thanks for your answers. FAST SDD's performance is more better.
That's correct.
Next question, continue. In recent years, more and more people in the SRF industries have been using SDD technology. What do you think? Is this just a performance improvement, or are detector standards changing more widely?
Well, I think it's really both. They're not separated. I think the FAST SDD delivers much better performance. Really, the FAST SDD has better performance across the board than silicon pins. But because the performance is better, that has enabled new applications and improved the standards of the measurements, and that's why it's being adopted across the industry. So the performance is so much better that it has become the standard, enabling new applications and new quality of measurements.
Okay. There will be more new applications. Yeah.
Yes.
Yes, that's good. Looking ahead, how do you see detector technologies involved over the last 5 to 10 years? And what new development might make the SRF analysis even more effective?
That's a great question, and as the chief scientist at AMPTEK, making new and better detectors is one of the things I'm absolutely involved in. And I really see 3 major things that we're focused on. One is continuing to make the detectors even faster, operate at higher count rates. So we want to push that technology to get higher count rates, improving this precision, faster measurements. The other thing that I think will be evolving is the ability to do better minor element detection, trace element detection. So there are a number of improvements we're working on to detectors to reduce the background so that you can detect even lower and lower quantities of elements. And the third thing that's interesting is so for the heavier metals, for example, platinum and gold, we today typically use the L lines, but the L lines exhibit a whole lot of overlap, so it's difficult to quantify them accurately. There's some interesting work going on instruments that would work at higher energies, and those will allow measurement of the K lines of these elements, which will greatly improve the detection limits and accuracy for the rare earth metals, for gold and platinum and elements like that. So I think all 3 of those are areas of current development, and yes, we'll be seeing new products addressing those things in the next 5 to 10 years.
Okay, thank you for sharing your views on detectors technology. Thank you so much.
My pleasure. It was good to talk to you and good to have a chance to talk to your many customers and users. Thank you very much.
Thank you very much. Thank you.